Hey everybody, welcome to our lesson video for 7.7. Today we're going to be still focusing on factoring, but we're going to be looking at factoring special products. You may remember back in 7.3 that we learned some shortcuts for multiplying binomials. Today we're essentially looking at this in the opposite direction. So the better that you learned those shortcuts the first time around, the easier 7.7 will be for you. So what I'd like you to do is take a moment to set up a note sheet with the section, the date, and the I can statement, and then resume the video as soon as you are ready. All right, so we're going to start by looking back at algebra tiles one more time to help make this shortcut particularly visual for you. So our goal is to solve the equation x squared minus 4 equals 0. And one thing I want to point out here is that at various times, we've solved different types of standard form quadratics where we've dropped different parts of the ax squared plus bx plus c equals 0. For example, earlier this chapter, we solved quadratics where we dropped the c term. And we just had quadratics like 6x squared plus 3x equals 0. We were able to factor to solve those. Today, instead of dropping the bx term, or the c term, we're looking at problems where we're dropping the bx term. We're just left with x squared minus 4 equals 0, which we can factor to solve. The way that we're going to think about this is start out by placing the x squared minus 4 into our algebra box. So I'm going to put in an x squared term. I'm going to put in 4 1 terms. And I'm going to put them in the corner because that would be typically where we would put our 1 squares. Now, what you're going to notice here is you're going to be looking at this, you're going to say, wait a minute, Dylan, didn't you always say that we had to create a complete rectangle? And I would say, yes, absolutely. That is what we said. We have to create a complete rectangle. So we need to put in the rest of our tiles in order to be able to actually do that. And so in this case, but we need to think about it because we need to put in our tiles in such a way that they would cancel out because clearly there's no bx term in this original equation. So the way that we might complete this rectangle is we could put in 2 positive x tiles as well as 2 negative x tiles. Because if we do that, we actually have the same expression because the positive x tiles and the negative x tiles just cancel each other out. So inside the box here, we still have x squared minus 4, but now we have a completed rectangle. And so if we actually write down along the sides what this means, or if I drag this in, on the top, our factor would be x plus 2. And on the side, our other factor here would be x minus 2, because we have to create the red along the bottom. And so our 2 factors for x squared minus 4 would be x plus 2 times x minus 2 equals 0. And so if we want to solve this, then we can use our zero product property to say x plus 2 equals 0 and x minus 2 equals 0. So x equals negative 2 and x equals positive 2. So you can see here that we can use algebra tiles to essentially visualize factoring this and working our way backwards. Now, of course, we'd like to have a technique where we don't need to use algebra tiles, and that's where our shortcuts come into play. Because if you remember, we learned the difference of 2 squares back in 7.3. Now we're just looking at this backwards. So in 7.3, we said a plus b times a minus b equals a squared minus b squared. So if we think about that in reverse, if we're given a squared minus b squared, we can factor it into a plus b times a minus b. So like as an example, if the problem was x squared minus 9 equals 0, our a term would be x, our b term would be 9, and so I apologize. Let me rewrite this slightly. Our a term would be x, our b term would be 3, because 3 squared is 9. And so if we factor it, a plus b would be x plus 3, and a minus b would be x minus 3. And then we'd be able to use our zero product property in order to solve to get our solutions of -3 and +3 for x. So we're going to look at how we can use this to factor and solve a couple examples here. And I would like you to see if you can pause the video and try these two examples first to see if you can come up with the solution to each of them. And then I will explain how to do it as well. So pause the video and try both of these, and then resume the video as soon as you're ready. All right, so for the first problem here, the first thing I might think about is I might try to rewrite this as x squared minus 5 squared equals 0, if that helps me identify that a is x and b is 5. And so then if I want to put this into a plus b times a minus b form, I would say x plus 5 times x minus 5 equals 0. And so then if I use our zero product property, x plus 5 equals 0, x minus 5 equals 0. So x equals -5 and x equals 5 would be the two solutions for this problem. Similarly, for the second one, the tricky part here was that you have to make it equal to 0 first, because that's what we always need to do with every single quadratic that we solve. So we would say 4z squared minus 1 equals 0. So now, in this case, it might be easiest to rewrite this in terms of perfect squares, because ultimately our goal is to find a squared minus b squared equals a plus b times a minus b. So I might rewrite 4z squared as 2z all squared minus 1 squared, just so that I can recognize that in this case my a value is 2z and my b value is 1. So my factors would be 2z plus 1 times 2z minus 1. And then we can use again our zero product property. 2z plus 1 equals 0, 2z minus 1 equals 0. So 2z equals -1, 2z equals +1, and z equals -1/2 or +1/2. So the key here was setting it equal to 0 initially, and then also recognizing your perfect squares. 4z squared is really 2z all squared, and 1 is really just a perfect square of itself. It's just 1. Sometimes you'll see some neat applications of this for math competitions. For example, you might be asked to evaluate the expression 54 squared minus 48 squared without a calculator. And that sounds nearly impossible, because you would have, if you had no calculator, and you were asked to evaluate 54 squared minus 48 squared, you would have to square both of them and then subtract them, which could be very time consuming. But if you know your special products patterns, this is actually an extremely easy problem, because if we have 54 squared minus 48 squared, then that just tells us that a equals 54 and b equals 48. So all we have to do is apply a plus b times a minus b, because we know that a squared minus b squared equals that expression. So then 54 squared minus 48 squared would just be 54 plus 48 times 54 minus 48. In other words, it would be 102 times 6, which is 612. So this is a really common math competition question because it's checking to see if you know your shortcuts and you know your sum and difference patterns. Because otherwise, yeah, this would be a pretty complicated problem to actually try to figure out. So the last thing that we're going to look at here is solving quadratics that contain fractions, which looks really difficult. But if we can fraction bust, like we talked about in pre-algebra, and get rid of all the fractions, then these problems become much easier. So for example, if we look at the first one, x squared plus 2/3 x plus 1/9. The first thing we want to identify is what the least common multiple is for the denominators of the fractions. In this case, we have denominators of 1 under the x squared, 3, and 9. So our least common denominator would be 9. And if we fraction bust, what that means is we multiply the entire expression by 9 on both sides. And if we do that, for this problem, we would end up with 9x squared. Now, 2/3 x times 9, the 3 and the 9 cancel out to become just 3. So it's really just 2/3 of 9, or 6x. And then 1/9 times 9 is just 1. And all of a sudden, we're back to a quadratic that's fairly straightforward to solve. And you could factor this one using either box and diamond or the split method, and then solve it rather easily. Now, the same thing here is true if we fraction bust for the other one as well. So w squared minus 7/3 w plus 49 over 36. The least common denominator here would be 36. So we would multiply the whole thing by 36. And we would end up with 36w squared minus 84w, because 36 divided by 3 is 12. 12 times 7 is 84. Plus 49 equals 0. Now, for both of these problems, there's something special going on here that makes these problems much, much easier to factor. And this is the other shortcut that we learned back in 7.3. So you could factor and solve either one of these using box and diamond or the split method. However, back in 7.3, we learned that a plus b squared equals a squared plus 2ab plus b squared. And we learned that a minus b squared equals a squared minus 2ab plus b squared. And we can use this in reverse to super quickly factor certain quadratics that are set up in this perfect squares system. So for example, let's start with number 2 first. 36w squared, we could think of, for 36w squared, that tells us that a is just the square root of that. A is 6w. And for 49, that's also a perfect square. So b equals 7. So then we just need to work in reverse. We're using the second one because there's a minus sign right here. But this tells us that this factors into 6w minus 7 squared. So if you remember your shortcuts, you don't need to do box and diamond or the split if you see perfect squares, which is super cool, because now we can just solve this and say, well, we know 6w minus 7 equals 0. So 6w equals 7, and w equals 7/6. And just to be clear, you would get the same answer if you used box and diamond or split. It would probably just take you a lot longer. And we can do the same thing for a as well, or for the first one. For 9x squared, the square root of that, so a is 3x, and the square root of 1 is just 1, so b equals 1. There's a plus sign in the middle, so our 9x squared plus 6x plus 1 would just make 3x plus 1 all squared. And then we would just use our sum and product property. So 3x plus 1 equals 0, 3x equals negative 1, and x equals negative 1/3. So again, both of these could be solved after you fraction bust by using your box and diamond or your split, but it's so much easier if you happen to really understand your shortcuts, and you can just use the shortcuts that we've learned to speed up your process. So that brings us to the end of our video for 7.7. Give the homework a try and let me know if you have questions.